At CECO-Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, CECO helps ensure you achieve real results. No matter your need, CECO has you covered. Simplify your environmental initiatives with our CECO Environmental family of industrial solutions brands. CECO Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, CECO helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit CECOEnviro.com today.
Welcome everyone, and thank you for joining us today to the CECO Certified Continuing Education Series. So today we'll be learning about pumps in water and wastewater applications presented by CECO Environmental. My name is Jen Bacus. I'm the Product Marketing Manager for Industrial Air and Fluid Solutions segment of CECO. With me today is Justin Folk, Application Engineering Manager, Michael Toy, Regional Sales Manager, and Steve Rose, Director of Engineering for CECO. So while we wait for everyone to join, I'd like to go over some basic housekeeping items about our webinar platform and PDH certification. So first of all, if you have any sound issues, make sure that you check your media player to make sure you're not on mute. Also, check the help widgets because it can help you, and give you some pointers on what could be wrong. Finally, last option is to log out and log back in using the link from the email that you received when you first joined. So now on the platform itself, so at the bottom of your screen are multiple application engagement tools, or like I like to call them widgets that you can use. All these widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area and maximize it to full screen by clicking on the arrows at the top right corner. If you have any questions during the webcast, submit them through the Q&A widget. To keep ourselves on track, we'll hold them off until the end of the presentation, but you can submit your questions at any time. And if we don't get to your question live, we'll make sure to contact you later. A copy of today's slide deck and additional help materials are available in the resource list, the one that looks like a little to-do list bullet points. We encourage you to download any resources or links that you might find useful. So, for example, there are links to CECO's LinkedIn, Facebook, and YouTube channels. We post all events on LinkedIn and YouTube and Facebook, sorry. So by following us, you'll be able to, keep informed of future webinars. The pumps in water and wastewater application summary is a very useful reference when you're taking the PDH quiz for the PE certification. And I really highly recommend having a look at it before taking the test. The PDH development hours of PDH state information is also listed. Right now, we're about to offer credits in 36 states in the U.S. And for the rest of the widgets, you can just hover over them and see what they are. For example, there is share via social or email as direct. The checkmark with the list will take you directly to CECO-Certified.com, where you will find your schedule and registration for all events scheduled and on demand. We have right now one event scheduled for next month on mist elimination fundamentals, and more coming every year. Finally, for anyone who is interested in PE credits, you want to have a look at the two last widgets on the right before the end of the presentation. So the test widget takes you to the quiz, and the tracker widget helps to see how far you are in terms of filling the requirements. Now, generally speaking, webinars are bandwidth intensive, so close any unnecessary browser tab in order to conserve your bandwidth. And if your slides are behind, try pushing the F5 key on your keyboard to refresh the page. And also Chrome seems to be the best browser for this platform. You will find any additional answers to some common technical issues located in the help widget at the bottom of your screen. Now looking at PDH, so the on-demand version of the webinar will be available after the event and can be accessed using the same audience link that was sent to you earlier. And all interactivity remains, including the testing capabilities. So today's webinar value is 1 professional development or contact hour, but you must be present for at least 50 minutes. This is both for our live and on-demand viewers. So if you get interrupted or you need to leave, no worries, you can come back for the on-demand version to complete the requirements. The second requirement is to complete and pass the test. So that means getting 8 out of 10. When you are done, you can go to the tracker widget and it will allow you to print your certificate once you've made the requirements. You can also come back later for the on-demand version to print. We suggest that you keep track of the events you attend, and CECO will keep records for 6 years. If you have any questions regarding the PDH overview or else, please contact Mary Resnack at mresnack@oneseco.com. So this webinar is 1 hour long, but we'll try to keep it open for an additional 30 minutes after the event to allow completion of the quiz and print any materials that you would like to print. So here's the outline for today's presentation. We'll do an overview of the water and wastewater market before going into the processes for wastewater treatment, water treatment, and desalination. And lastly, we'll do a deep dive into the pumps used in these processes. So I'm going to pass it on to Justin now, who is going to highlight some interesting facts about the water and wastewater market. Justin, it's all yours.
Thank you, Jen. To get us started, we wanted to provide a high-level overview of water and wastewater, its place in the market, the physical volume that we use of water as individuals and as a society, and just how involved the infrastructure associated with all of that really is. The water and wastewater market is a big and growing market. As we get into the presentation, we'll be touching on some key reasons why it's such a big market and why we are experiencing a growth of over 170% globally over an 8-year period. Such reasons as infrastructure improvements required to reduce waste, operational efficiency improvements, reducing our carbon footprint and overall environmental impact, and I could go on and on there. So in addition to that, there's a variety of other markets, not just water and wastewater markets, that is associated with the wastewater market directly and indirectly, such as the chemical market, and we're seeing the correlated growth in those markets as well. So here's some just high-level overview facts, which some of these may be a little bit surprising unless you do a lot of Googling. For example, here, this first one, each American uses 82 gallons of water a day in their homes. That was a lot more than I realized. And then looking at the next one there, you'll see 22 trillion gallons per year of wastewater generated in North America with 16.1 trillion of those treated, which that just makes me wonder what happens to the other 6.4 trillion gallons. Well, reducing that number is part of why the wastewater market needs to and is growing at the rate that it is. The next point there, 80% of water used in the U.S. is for irrigation or thermoelectric power plants. That only makes me think of just how much water it is that is being used. If individuals are, under the 20% mark, and 80% is used for just that industry, it just makes you think of how much water we're really using. Then you've got some other interesting facts here, including almost 1 million people in the U.S. cities lacking sustained access to basic sanitation and wastewater treatment. And then a little bit over 500,000 people in U.S. cities lacking sustained access to clean water. Water and clean water, I should say. And then if you look at the visual on the right, when I see this, all I can think is, when I look at the numbers on the left, it just makes me think, me as an individual, how can I be reducing this? And if there's certain aspects of this that I can't reduce, I really do hope that we as a society are doing a good job of reusing this and capturing all of this water that we're using. So I'm going to break a presentation PowerPoint rule here, and I am going to do some reading off of this slide. But the reason for that is I'd like you to pay close attention to the visual that's on the left side here, just as an overall understanding. And this doesn't address everything, and it definitely doesn't get into all of the fine details of each of these, but it does give you a good visual understanding of all of the ways that water is used in our society these days and where it goes, where it comes from. So let me read on as you continue to do some studying of that visual. So I want to describe the difference between water and wastewater and the types of treatment. So wastewater treatment refers to the physical, chemical, and biological processes used to remove pollutants from wastewater before discharging it into a body of water. On the other hand, water treatment refers to raw and untreated water obtained from an underground aquifer, usually through wells, or from a surface water source, and then it's pumped or flows to a treatment facility, ending with potable/drinking water. So again, just to highlight that visual on the left, it just makes you wonder, like, how big this infrastructure is, how it's all tied together, and are we as a society doing everything that we can to ensure that we're making the right decisions here and capturing the water as best we can and not wasting water. And here is a poll question, and I'm going to pass it back to Jen.
Thanks, Justin. Thanks a lot. So yeah, we're up to our first poll question. You'll be able to answer the question in the next slide. Just hold up for a second here. So this question is, how much experience do you have with pumps in water and or wastewater applications? So either A, I'm an expert, B, I have some experience, C, I have little experience, or D, I didn't even know pumps are used in water or wastewater applications. So here on this slide, you can place your answer, and I'll just hold on for a couple of seconds while you do that. And after selecting your answer, don't forget to hit the submit button. All right. So let's see what are the answers at this point. Oh, very interesting. So we have a few of you that are experts and over 80% that have some experience. So that's really good because this presentation will go a little bit deeper into the pumps. But even for those that are, in the C categories of discovering this, we're still taking a high-level approach. So I think all of you will find this very beneficial. Okay, so fantastic. Now I'm going to pass this on to Michael, who's going to get into the meat of the presentation with wastewater treatment. Michael?
Good afternoon, everyone. Hopefully everyone's doing fine. Justin, great job on the start of the presentation. As you can see, it's a really big topic, or big topics, or set of topics. So we try to kind of narrow it down into kind of what makes sense from a real high-level view. So I'm going to start off by talking about wastewater treatment process. Really starts on this slide talking about conventional treatment plants, the sewage treatment plants, STPs, which is your typical treatment plant that you'll find in a large city or municipality. Usually raw waste, sewage waste from households, buildings, etc. And then there's effluent treatment plants, or ETPs. This is clean industrial wastewater. Activated sludge plants, similar to sewage treatment, predominantly using activated sludge to digest biological contaminants. And then the fourth is common and combined effluent treatment plants, really a lot based on effluent treatment plants for smaller wastewater generators. So it's like I said, we're going to look at kind of at a higher level on a conventional STP or sewage treatment plant. So it's kind of broken down, and we started looking at what's wastewater treatment plant. We kind of looked at it from an industrial and on a municipal wastewater perspective. And industrial wastewater, although a lot of the components are the same in between the two, it really covers the mechanisms and processes used to treat wastewater that's produced as a byproduct of whatever commercial activities are happening. In a lot of cases, the industrial wastewater is then converted to either reuse inside a process at a mine, power plant, cooling water, that kind of thing, or it's released to a sanitary sewer or back into surface water in an environment such as a river, stream, lake, aquifer. Municipal wastewater is a little different. We commonly refer to that as a sewage treatment plant, where water is treated for to remove a lot of solids, and it's conveyed in combined sewer or sanitary sewer and treated at a wastewater treatment plant. So we're like I said earlier, we're going to separate kind of wastewater and wastewater treatment from water treatment and kind of keep those separately. And although in some cases that they're the same, but for our example today, we're going to talk about wastewater treatment plants discharging their effluent into lake streams or aquifers. When we looked at this fairly significant market, and one we're all used to and don't quite understand as much as we probably should, I know that's the case for me. I really looked at trying to break down the sections of pumps and wastewater and where they apply, and there are a plethora of different types, and of course a plethora of applications that relate to where these pumps are applied in both from a centrifugal and a positive displacement standpoint. We're not going to go through this a lot in detail. There's a lot of information here, but there's primarily two basic pump types that are used, centrifugal and positive displacement. One of the things, at least in Canada, I'm not so sure it's the same in the US, is combined versus separated sewers. Combined sewers carry both stormwater and wastewater, and separated sewers are either sanitary sewers or storm sewers. That makes a huge difference, as we have issues in town cities, especially around our coastal cities, where our storm sewers or our sanitary sewers are overflowing, and storm sewers now are being contaminated with human excrement and things that shouldn't be in our water streams. So the part of the growth in water wastewater overall is looking at kind of migrating more to combined sewers so that all water is treated, not just sanitary sewer water. A couple of interesting things that we've learned along the way is the difference between influent and effluent. Influent is the water that flows in, so raw, untreated water. Excuse me. And effluent is the sewage or industrial liquid waste that is released into the natural water by sewage treatment plants or structures to treat industrial water. So kind of interesting. I always thought effluent was meaning the same thing, regardless of application or process within the wastewater treatment process, but it's not true. So let's get a definition of wastewater treatment. A treatment plant is uses of a series of treatment stages. There's primary and secondary clean water so that it is safely released into a lake, river, or stream. So we're looking at a waste treatment plant not to have the additional stages and purification to that of drinking water. We're looking at it from a perspective of waste treatment to take influent and allow it to be effluent to be able to release in a number of ways, and that could be to a waste treatment facility. So primary treatment removes about 60% of the suspended solids from water. It also involves aerating, putting into the wastewater, putting oxygen back in, screening, pumping, aerating, moving sludge and scum, killing bacteria, and handling wastewater residual solids. And then the secondary part of the treatment removes 90% of the suspended solids. Oh, excuse me, it's dry in here today. If we look at a wastewater treatment plant, here's a picture of a typical wastewater treatment plant, kind of broken down into 10 primary steps. I'll take kind of a quick deep dive into what these steps are through the process on the next slide. It really starts with wastewater collection. So that's from industrial and municipal storm sewers, wastewater and sewage on the influent. So it's collecting all that and making sure it gets into the actual wastewater treatment plant itself. And then a real important stage is screening and grit removal. And this is really moving the water through screens to separate the larger trash and solids. A third part of the process is primary treatment, or primary treatment / clarification. This is basically settling. It allows materials to settle to the surface and scrape off and be disposed of as a treatment after drying. And the fourth component is odor control. This is something over the last 25 years that's really gained a lot of ground, especially as wastewater treatment plants are being surrounded by residential areas. So the need to reduce odors is becoming more and more pronounced. Aeration is the fifth step. Provides oxygen to bacteria for treating and stabilizing the wastewater. Real important step in the process to break down organic matter and to containing carbon and form carbon dioxide in water. The sixth step in the process is sedimentation. So this allows particles in suspension to settle out. The seventh step is sludge removal. So the solid material settles and it's removed and allow bacteria to act in organic matter to help decay the sludge removal. And there's a whole secondary process related to sludge removal. And again, each of these steps in wastewater treatment, we can actually do a specific presentation dedicated on. But there's a whole secondary section to sludge removal. And then filtration, after the water is fairly clean, it goes through SAM, for example, to release bacteria and take out the rest of the contaminants or solids. And if the ninth part is digestion, hold and heat the solid material to break it down into nutrient-rich biosolids and methane gas. And the last step in the process, which is kind of near and dear to our heart, is disinfection. Water is treated with chlorine primarily to kill bacteria. There's a number of different steps which we'll talk about in further slides. But it's an important element in the process steps as well. And again, there could be a whole section just on disinfection. Jen, over to you.
Thank you very much, Mike. All right, so we are at our second poll question. So this is just to tease your memory. We covered this like a few slides ago. What different types of water are there at a wastewater treatment plant? So answer A, white water, B, gray water, and C, black water. So once again, this is where you can submit your answers, and don't forget to hit the submit button. I'll just take a couple seconds here so you can fill in your answers. Alrighty, let's have a look at the results. Perfect. So I see everybody put either gray water or black water. So these are the two types. One is effluent, one is influent, and but white water is not the same. So perfect. Thank you so much for everybody for taking the poll. I'll just switch it over to Steve. Steve, you can go ahead and talk to us about water and desalination processes.
Thanks, Jean. Thanks, Mike, for the lead into this. I'm going to touch on water treatment process, very similar to the wastewater treatment process Mike just talked about. As you can see on the left there, or the right, excuse me, there's 5 or 6 steps in the process, where in the wastewater treatment there's a few other added steps because of the nature of the fluid or the intake fluid coming into the process. There's 2 different pieces of the water treatment process, or types of water treatment, that we've split out to look at separately. You have fresh water, right? Water coming from rivers, lakes, aquifers, wells, reservoirs. And then you have water treatment that's associated with salt water and desalination. We're focused on potable water at this point when we're talking about water treatment in our overview here. Potable water has several end uses out of this process. You have, obviously, drinking water. Some gets used for industrial with respect to washing processes, cooling towers and cooling type processes, and other types of industrial uses. Again, irrigation is another end use. Obviously, we're very much dependent on water and irrigation, and from a food perspective. And then you got water recreation, again, pools, parks, things of that nature. And then you also have the last one there is ultra pure water. Ultra pure water is typically found in processes where very sensitive to very, very small amounts of contamination. So that would be semiconductor, pharmaceutical type applications, but not used for human consumption. Ultra pure water is not good for drinking water, and quite unhealthy. Quick definition: water is or treating the water improves the quality of water to make it specific to the end use, as I just described. The treatment process is fundamental to human health and our well-being as a society. And as I mentioned, the overall focus of this is going to be taking water, raw water, to and then cleaning it to a potable use application. So water treatment plant, very much similar to the picture showed before. Again, a little bit less infrastructure to support water treatment than wastewater treatment. Again, very important to us as a society. Clean water is just a really important topic in general. As mentioned before, 82 gallons a day used by a household in the U.S. And globally, it's somewhere around 16 gallons a day. There's no lack for the need of clean water every day around the globe. So we'll start with some of these treatment processes at number one, raw water intake. And as I mentioned before, there's a reduction in steps, so a little bit cleaner as far as the process goes. Raw intake water can be anything from an aquifer, as mentioned, and that water is pre-treated through a set of screens and some pre-filtration to remove the coarse solids. Very similar to the intake pump or intake process on a wastewater treatment. There's different pre-filtration taking place to get rid of the big items. Once we move on from the raw intake, we get to coagulation and flocculation. This is to create a condition in which the smaller particles in the water and undissolved solids are able to flock together to form bigger solids, which then are more easily removed from the process. So after flocculation, the water moves into a sedimentation or clarification step. In this step, those solids are dropped out due to gravity and mixing, and then they are shipped off to or sent or pumped to a solid handling dewatering process that's not shown here. Obviously there's some waste that comes from the water treatment plant. That waste is dealt with in a different way. We're not going to cover that here today. Once you go from sedimentation and clarification, you move on to filtration. Again, whatever doesn't come out of the water during the sedimentation process. Again, there's another set of filtration processes that take place. Again, different filtering steps, and again, depending on the source of the raw water, the type of filtration required may be different from plant to plant. But types of filtration you see here in this step are sand filters, gravel, even some carbon filtration to get the water as clean as possible at that step of filtration. Once we get the water very clean as far as solids go, you go into that disinfection step, and as discussed before, this is where we get rid of all the bugs, the pathogenics that cause waterborne diseases that none of us want to catch when we're drinking water. Chlorine's typically added, or chloramine, which is a chlorine and ammonia mix. In some cases, you'll see ozone being used possibly in this step, or ultraviolet radiation at this step as well. Typically not in a large scale plant because of the cost and the size of that type of equipment to treat so much water running through the plant on a daily basis. The final step is storage and distribution. All that water has to be kept somewhere. It doesn't go straight to your house. It's put in tanks or below ground, above ground tanks, water towers, and kept there for everybody to start using when they're ready for it. I'm going to go ahead and skip this slide, everyone. That was summarized in the one previous, but these are the steps I went over. here for reference in the future. So we're going to move into desalination now, but there's some interesting facts to share, again, to just emphasize how important this topic is. Over 1% of the water on Earth is fresh water that's easily accessible. So that's the water we're getting from aquifers, rivers, lakes. And then there's some fresh water that's not easily accessible on a regular basis. That's the water that's tied up in glaciers, things like that. And then the other 97% of water is all some sort of salt water or brine that's, mostly related, found in the oceans around the globe. So obviously desalination is really important to us as a society moving forward with population growth. There's always going to be a growing need for clean drinking water, and a lot of that's tied up in a fluid that's not drinkable in its raw state. So desalination is extremely important to us. Some other fun facts here that are pretty interesting that I know I didn't know until I started digging deeper. 1 in 10 people in the world lack a source of clean drinking water. That's sort of mind-boggling in and of itself. So a quick overview of the desalination process. Again, it's not entirely different than what we just spoke about at the first part of the process. We'll get that into a minute. Get to that in a minute. Currently, approximately 16,000, currently there's a 95 million meters cubed per day of water coming from desalination from 16,000 operational desalination plants in 150 countries. So desalination is a big part of what we're talking about as far as treating water. And they're treating 95 million meters cubed per day. That's 17 million gallons per minute. But in the public water systems, which are mostly the traditional water treatment system I just discussed, there's over 34 billion gallons of water a day produced. So desalination is just touching the water treatment piece, with respect to gallons per day or gallons per minute. There's a lot of water that could be taken from desalination that's not today, or clean water, that is. So desalination can take place two different ways. You got there's a thermal method, and there's the sort of the electrolysis method, or electrodialysis method, and part of that's reverse osmosis. Desalination by thermal is multi-stage, where you use heat to boil the water, or evaporate it and then condense it again, where the solids boil off and the clean water condenses. More than half of any desal water comes from that method, which is very interesting. And the other half is most of it's coming from the next one, which is membrane process. The OR process that we mostly know is the most common. There's a freezing desalination process, which is where you crystallize or freeze the fluid. Not scalable from a day-to-day use type method. Geothermal, and then you have solar distillation again. Not very scalable. A lot of land required to do that. More like a off-the-grid home type process that's used. So you have in the membrane process, just to re-emphasize, you have the need for more energy. It requires electricity to in the electrodialysis process. It requires electricity to separate out by producing a positive and negative charges to get the salt out of the water. And then reverse osmosis, which we'll go into detail here, will also it uses more of a filtration method to do the same thing. Desalination, again, it's just a reminder. It's where we move solids out of salt water through a couple different methods, distillation or a membrane process. And most of the activities today are focused around desalination and making them more cost effective. Again, these are more expensive processes to operate as compared to a traditional wastewater treatment plant. This is a good view of a desalination plant. Again, fewer steps than wastewater. Step one is your seawater intake. In this case, they're taking it through a well that's sourcing it from the water there at the top of the picture. They can take the water directly out of the ocean or out of a bay or out of a lagoon, but that's what's happening there. That process again has a pre-filtration. It's pumped in. It goes through several types of filters and strainers to take out the big stuff, which allows it to move to pre-treatment, or that is pre-treatment, and then it gets it clean enough so it can move into the reverse osmosis process, which is number 5 here. Or reverse osmosis pushes the feed water under high pressure through a semi-permeable membrane. The passage of water molecules, or allows the passage of water molecules through, but not the majority of the dissolved salts or organic materials or bacteria that are in the water. Again, a very high energy requirement process. So again, your costs tend to be higher on this type of plant. The next step is conditioning. Again, much like before, this is where the chlorine's added. I didn't mention it before, but maybe fluoride. So we're trying to kill off the last amount of bugs that remain. And then we go to storage. Again, it doesn't go directly to your home. It sits in a tank or a water tower somewhere that then flows into our homes. And then finally, number 8 out here, there is waste that comes off of this process, some in the form of solids, in between steps 3 and 5, which is taken off and produced, a sludge is removed. And then after it's all said and done, the brine is pumped underground out to sea, or it can be piped overground, but in this case it's a tunnel or a pipeline that's dumping the brine from the final end of the process into the ocean. Again, this is a slide that covers what I just went over.
All right, thank you so much, Steve. We are at our last poll question, so that's an easy one. I'll just switch over to the answer so you can fill it. So what is the percentage of the Earth's water that is salt water? Either 90%, 97%, 100%. I'll wait really a second, sorry. All right, so let's have a look at the result. That should be an easy one. 97% majority. So the answer is 97% of salt water. So that's why it's so important to look at desalination processes. All right, won't take longer. Mike, take over and talk to us about pumps.
Well, good afternoon again. One of my favorite subjects in the whole wide world is talking about pumps. So, we've got some good information to share with you, kind of related to the topic of today's meeting. I hope you found the information we provided so far useful and informative. But let's talk about pumps. I'm going to do a high-level overview based on pumps used in water and wastewater. So, a pump is a device that moves fluids, liquids or gases, and sometimes slurry by mechanical action, typically converting from electrical energy into hydraulic energy. Pumps operate by some mechanism, typically reciprocating a rotary, and consume energy to perform mechanical work moving fluid. That's pretty straightforward. I think that's out of the Webster's Dictionary. A few important things as it relates to pumps. One of the previous CECO Certified webinars, we focused on centrifugal pumps. So you can find information if you're looking for more information on centrifugal pumps specifically on our CECO website. Not all pumps can move fluids. Not all pumps can move gases, at least effectively. Some pump types can move liquids containing solids. Some types of pumps can move slurries without solids. When I look at pumps in specific applications, I refer to that as fit for purpose, when the pumps are designed and engineered for a specific purpose. And you'll see in the following slides how that really applies to some pumps in wastewater and in water that aren't necessarily used in a lot of other applications, or they're used in applications which are very similar to the purpose that they're designed for in this example. Most of the time, from a specification standpoint, those are end user specific or design engineering specific. There's a number of ways to accomplish a single application or process on a number of different pump types. There's one major exception in the United States and somewhat in Canada, as we follow a lot of U.S. certification, is potable water or drinking water needs to meet NSF, and I'll talk about that in a second. So what is NSF? NSF was founded in 1944, called the National Sanitation Foundation. It really is about creating and maintaining rigorous industrial standards. One of the standards is NSF ANSI 61, and really has to refer to drinking water system components and standards for which they must meet. Part of that specification obviously relies on, or is specifically related to pumps and how they're constructed, materials, that kind of thing. So for the most part, there's no real standards as far as what pumps are placed in particular applications related to water, wastewater, except when we start talking drinking and potable water. So let's talk about pump types in wastewater treatment. Really, again, there's two primary types. One is centrifugal, and two is positive displacement. Centrifugal pumps are by far the most common in any industry, representing about 82% of total pumps consumed in any application, which is probably a little higher percentage when we start talking about pumping sewage and effluent, or influent, excuse me. A lot of these pumps are installed in pits and sumps and can easily transport suspended matter, as in sewage. Some of the pump types that you will see in wastewater treatment are axial flow, submersible grinding pumps, vertical sump pumps, solids handling, self-priming, non-clog, chopper, shredder, recessed vortex impeller pumps, through impeller pumps, and vertical turbine solids handling. Again, remember, this is referring to wastewater treatment. But in addition to centrifugal pumps, there are applications that are better suited with positive displacement pumps. Some of those are reciprocating, rotary lobe, progressive cavity, and diaphragm, whether that be mechanical or air. And again, think back to the original portion of this excuse me, presentation when we were talking about, how big this market is and how each individual segment of the process steps can be a presentation on its own. We can get much more specific. But in this example, we're just going to kind of run through these types. The most common or very common pump in regardless if it's influent or effluent in wastewater treatment is submersibles. Now there's a number of different types of submersibles. There's sewage and wastewater, whether that's used water from your sump pump in your basement to outside to in a canteen to move your sewage. There's submersible chopper pumps, which are used to handle larger concentration of solids and are hard solids, and they actually chop up the media. And grinder pumps, which are similar to chopper, only they just have a grinding medium on the impeller that helps break down the solids. Axial flow pumps. Axial flow is also called a propeller pump. They move fluid actually through an impeller. They provide high flow rate and low head. And they can be semi-adjustable by adjusting the pitch. Not necessarily solids handling, but they move a lot of wastewater. The recessed vortex impeller, also called a recessed impeller pump, are basic principles creating vortex flow with having the impeller recessed, which is outside of the path of the liquid. Again, very common, very handling stringy solids, very common in wastewater. Mixed flow, impeller discharges fluid in a conical direction using a combined radial and axial pumping action. And finally on this slide, a screw impeller. A screw centrifugal pump combines the advantage of a screw pump with the advantages of a centrifugal pump. And it's very unique and effectively handles thick sludges or large stringy solids, shear sensitive fluids, and delicate materials, but becoming more and more common in wastewater. We talked about submersible pumps. Submersible pumps are ideal if you want to mount them in a sump, whether that's a dry sump or a wet sump. But in some cases, you don't want to mount your pump in the pumpage or have the means to have a dry sump, so you have it horizontal, surface mounted, and you have a solids handling self-priming pump, which makes it, depending on the application and how it's installed, it makes it a lot simpler, and you can mount it above the liquid, and it's designed in such a way that it's self-priming by design. Another very common pump is vertical non-clogs. As you can imagine, again, it's a version of recessed impeller pump or a specially designed open rotor. Again, a very specific kind of fit for purpose for pumping abrasive solids and slurries in a vertical concept. Solids handling vertical turbine. These pumps are specifically designed to pass solid sludge, trash, and long stringy materials. Vertical turbines are often in conventional wastewater applications where you need to move a lot of flow and a lot of volume. Used in water applications as well. Chopper shredder pumps. These are, we talked about them earlier in the submersible versions, but there's also horizontal and vertical configurations of choppers and shredder pumps as well. So as you can imagine, with what's in your Influent, you need to facilitate chopping or macerating solids. I will quickly run into pumps in water treatment. Again, it's fairly similar. You've got two primary types, centrifugal pumps or positive displacement. Again, in this particular market or this market segment. Centrifugal pumps are far more used to a greater extent than positive displacement, but there are applications where positive displacement pumps are used as well. So again, we'll go into them on the next slide a little more, but the vertical turbines, submersibles, cell primers, horizontal split case, vertical sumps, mixed flow, propeller pumps, and suction, general purpose, and ANSI. If you go into a water treatment plant, you'll see pumps of all kinds of variations and descriptions, but there are a few that are specific and fit for purpose. And on the PD side, reciprocating rotary lobe, progressive cavity, diaphragm, peristaltic. We talked about vertical turbines a little while ago. The differences here, they're not fitted exactly the same because they're not going to worry about solids. Again, moving high flows at medium heads. Submersible pumps are also common on the water treatment side. As described earlier, we don't worry too much about solids in this particular treatment stream, but the configuration and how it's mounted is beneficial and can be fully submerged in the fluid. Cell priming pumps, as we described earlier, although this is not necessarily solids handling, but it's the same concept where you have a suction lift and you don't have the ability to have a pit or a basin or a sump. You can have a pump laying horizontal and being able to provide a suction lift. If you want to move a lot of fluid, a horizontal split case is commonly used. As the name implies, the casing split into two separate chambers. This configuration on suction and discharge flanges is available as well, but ideally it moves a lot of fluids. Vertical sump pumps, they're actually used in, both the water side and wastewater side. And in this case, when we look at in industrial wastewater, they're used for a lot of runoff applications, especially industrially, even in your home, that kind of thing. But they're intended for in pumping applications to pump clean or lightly contaminated liquids. They can do fibrous slurries and liquids containing solids depending on the specific design. Propeller pumps are generally handled to movement of high volume of water at low discharge pressures. Excuse me. Again, pumping water from sources including lakes, ponds. So again, high volume, low flow. And suction pumps, as the name implies, the suction's on the end of the pump, applicable to most standard applications where standard fluids need to be moved. ANSI pumps, regardless of the application, they can be NSF 61 or not, depending on if they're pumping potable water or not, but common within the water process. It can either be horizontal mag drive or vertical. Mag drive, generally speaking, on the chemical side, which we'll talk about in a bit. Positive displacement pumps. So positive displacement pumps displace the same volume of liquid at any given rotation or stroke. The flow at a given speed remains constant regardless of changes in discharge pressure. So the big thing here is capable of pumping higher viscosities. So reciprocating pumps are positive displacement pump that works on a principle of movement of the piston in a forward and backwards direction. Common designs are piston diaphragm, and plunger. Excuse me. A common piston diaphragm designs are mechanically actuated, hydraulically actuated, and you'll see those in dosing, metering pump applications. We're running a little long here on time, but there's a section that I have on chemicals and pump applications with chemicals. One of the biggest usage of a piston diaphragm pump and hydraulic actuated metering pumps are in pH control as well as disinfection. And then there's special design plunger pumps that are designed specifically for high solid concentration waste. One of the busiest, or one of the most common PD pump types in in water and wastewater treatment is progressing cavity pump. Can handle solids. Can handle slurries and then influent containing solids. Very practical, very common in most wastewater treatment plants. Peristaltic or hose pumps. These again are fairly common. Again, depending on the application, they can handle train solids without any damage of the pumping components. And smaller versions on the peristaltics are a lot of an application are used for metering. Excuse me. And then rotary gear, whether that's internal, external, they move pumps with enclosed fixed volume, interlocking cogs or gears. Again, gear pumps commonly used for pump meeting high viscosity fluids, polymers, flocculants, etc. And again, the type all is dependent upon the customer, the application, and the design engineer that's working on that specific application. I'll just take a quick foray into, there's a couple of sections that are fairly important to us. One, I talked about this earlier, about odor control and how that particular segment of the process is growing. Wet air scrubbing is one, and it's one CECO takes a big part in. We have a scrubbing division, but we also supply, both with our Fibroc brand and Subco brand, pumps into that market from a chemical compatibility standpoint. Another section that we talked on briefly is disinfection and chlorination. A huge part of the water treatment process, whether it's waste or potable drinking water. It's really designed to kill or inactivate microorganisms in wastewater and making sure and pathogenic organisms. It's really essential to make sure the drinking water is safe for human consumption. In the process, there's pathogens removed along the way. Chlorination removes the last 1 or 2%. Extremely important. But there's other forms of disinfection. Here, from a pump perspective, we're looking at chemical transfer applications, whether that's centrifugal, as in a Fibroc pump, or which I mentioned earlier, dosing or metering applications, where you want to have a specific volume of liquid put into a line or a process at a specific rate over a certain amount of time. Jason alluded to this early in his presentation about chemicals and the effect of chemicals in the growing part of wastewater and how the chemical portion is growing. Well, here's a list of common chemicals that are in. Here's a list of chemicals that are typically in water and wastewater applications. As you can see, there's a lot of them. And why is that important? Because as we just looked at, excuse me, standard pumps in water wastewater, there's a lot of fit for purpose. In this specific area of chemicals, there's a lot of there's a lot of fit for purpose pumps that are designed and to put into applications where chemical compatibility is important. And for us, chemical and corrosion is a big issue, because one of our primary lines is either thermoplastic or FRP. So corrosion is a big issue. It's a big issue in water and wastewater in general, but it's a major issue when we start talking about different compositions of chemicals and their effect. So I think I'm just about out of time here.
Yeah, exactly. So sorry to interrupt you. There is one more slide, and you guys can look at it because we have all the slides in the resources, but I wanted to be respectful of everybody's time. So we will tackle one question, once again, related to the time limit here. Quick reminder, so to get the PE credit, you need to be here for at least 50 minutes, and you need to complete the quiz with at least 8 out of 10 questions. On the platform itself, So in the resources widget, I would highly recommend going to the summary and reading it because it helps out with the quiz. And also there is, as I was saying, a copy PDF of the slides, so feel free to download them. Once you've completed the quiz and been here with us for 15 minutes, there will be a pop-up screen that will show up where you can print your certificate for the PDH portion. All right, so that was it. So there is one question I think that, Steve, you wanted to tackle?
Yes, we were asked about why ultra-pure water was not fit for human consumption. When you purify water to that level of purity, the water takes on a negative charge. So when it so that means it's removed of all the good minerals that we want out of the water when we drink it: magnesium, calcium, potassium. So that's one reason. But the other reason too is if you were to drink that water, the minute or the second it touches your mouth, it's going to want to start leaching out those positive charged minerals from your mouth and other parts of your body. So again, you're sort of removing the good stuff when you put that ultra pure water back into your body. So that is why it's not fit for human consumption.
All right, perfect. Thank you so much for that answer. So now we're going to, be quiet, but I wanted to thank you, Justin, Steve, and Michael, and also thank you everyone for attending here today. We hope you'll join us for our next event on June 23rd on mist elimination. You can go to CECO Certified to CECOcertified.com, or the widget with the leaf and the check mark at the bottom to sign up for that. Otherwise, that's it. We're going to be quiet. The platform will stay live for another 20-25 minutes, just so you can finish up the test and the certificate. Thank you, everyone, so much for coming. We hope you have a wonderful day. Take care.